Yeah, no, but then get this. Then he said rectum darn near killed him. Yeah. Oh, whoa, hey, didn't see you there. Anyway, time for some combustion analysis. All right, so let's review combustion analysis. So I got a practice problem we can go over. And so hopefully you remember this all the way back from the beginning of Unit 2. Because the Unit 2 test is coming up, and you need to be able to answer questions like this. All right, so let's do it. All right, so if we're looking at this question, we're told that citric acid is a compound that contains carbon, hydrogen, and oxygen. So the compound has C, H, and O. We take 20.1 grams of citric acid and we burn it completely in oxygen. And we figure out how much CO2 is produced and how much water is produced. And from this information, we want to find the empirical formula of citric acid. Then, given a little bit more information, we want to figure out the molecular formula of citric acid. And then once we have the molecular formula, we want to write the balanced combustion reaction. And then we got a little stoichiometry problem at the end. Once we have our balanced equation, we can answer that question. All right, so let's go ahead and answer this question. All right, so let's understand what we're trying to do. We have a compound, it's got carbon, hydrogen, oxygen. We don't know the subscripts. And so let's remember subscripts is equal to moles. So if I can figure out how many moles of carbon I have, that'll be the carbon subscript. If I figure out how many moles of H I have, that'll be H's subscript, and the same thing with oxygen, okay? And so that's our goal. So given the amounts of CO2 produced from the combustion reaction and the amount of water produced, we want to figure out these subscripts so we can get our empirical formula, all right? So let's go here. This is kind of the way to visualize what's going on, right? So we got our citric acid, we don't know its subscripts, plus O2, burns in oxygen, O2, yields CO2 and H2O. We're told how much CO2 we got, we are told how much H2O we got, and we're told how much of this completely reacted. So if we wanted to figure out this mass of oxygen that reacted here, it would just be this plus X equals this plus this, right? Oh, we'd have to figure out the mass of this. And then if we figured out what grams of this was, we would say grams of this plus grams of that equals grams of this plus X. And that would give us how much O2 reacted. Okay, so in this problem, a couple things. We need to understand that all the carbon that started in the citric acid ended up in the CO2. So if we can figure out the amount of C in CO2, that's the amount of C in the citric acid. Same thing with the hydrogen. All the hydrogen here ended up in the water. So if we can figure out the amount of hydrogen in the water, that would equal the amount of hydrogen that started in the citric acid. But we can't do that for the oxygen because we have two sources of oxygen on this side and two places it went to, right? So even if we figured out the amount of oxygen here and the amount of oxygen here and added them, that wouldn't be the amount of oxygen here. We would have to subtract that amount of oxygen, and then that would leave us the amount of oxygen there. So there's a couple ways you could do it, but the oxygen is just a little bit more complicated. All right, so let's go through what you should do. So first I'm going to find the C in CO2, and that's the C in the citric acid. So we would take our volume of CO2 gas produced. We were told it was at STP, so we would divide by 22.4 liters per mole, and that would give us moles of CO2. And then we know that the subscript of carbon is 1, so 1 mole of carbon for every 1 mole of CO2. That gives us moles of C. Now, what I'm doing here is a little bit of an extra thing because I know I'm going to need this to figure out the oxygen later. Okay, so moles of C, that would be my subscript for C. But what I'm also going to do is go ahead and multiply that by the molar mass of C, which is 12.01. And that'll give me grams of C. So this is how many moles of C I have, this is how many grams of C I have, and that'll come into play later. If we didn't have oxygen in this compound and this was just a hydrocarbon, there would be no need to do this part, right? But because I know that I got that oxygen going, I'm doing this little extra step here. So we figured out moles of C, that's our subscript for C. All right, so we got one subscript, let's figure out the next two. So the next thing to do would be to find the H in H2O, and that would be the H in citric acid. And so here, this is where we got to be careful, and that's why I like showing the stoichiometry. Because like, moles of CO2 is moles of C because it's a 1-to-1 ratio. But moles of water is not moles of H because it's a 2-to-1 ratio. So we would take our grams of water, we would divide it by the molar mass, that would give us moles of water, and then we have to recognize that there's 2 moles of H, singular, for every 1 mole of H2O. So this is how many moles of H we have. And again, just like I did with the carbon, I'm going to take the moles of H and multiply by H, molar mass, not H2. So this is hydrogen, but it's not H2 hydrogen, it's just H. So we would multiply by 1.01, and that would give us grams of H. So we got moles of H, we got grams of H. Moles of H is the subscript. So now we got our 2 subscripts. We got the carbon subscript, and we got the hydrogen subscript. We just need the oxygen subscript, okay? So the reason why I figured out the masses of H and C is because we were given the initial mass of citric acid. It was 20.10 grams. And we know citric acid has carbon, hydrogen, oxygen. And we know of that 20.1 grams, now we know 7.54 grams was carbon, and we know that 0.854 grams was H, hydrogen. So if we just subtract, that'll give us how many grams were in the grams of oxygen are in the citric acid. So that's what we're going to do, okay? So again, now our goal is to figure out the subscript of O. So the first thing we're going to do is figure out what mass of that citric acid was just O. All right, so we do the total mass of citric acid minus the mass of the carbon that we found, minus the mass of hydrogen that we found, and that gives us the grams of oxygen. But be careful here. That's the grams of O, but remember, subscript is moles, not grams. So if we take our 11.71 grams of O and we divide it by the molar mass of O, not O2, the molar mass of O, that gives us moles of O. And so that's our subscript for O. So boom, right? We found our subscripts, 0.628, 0.845, 0.732. So those are our subscripts. And, obviously that's not an empirical formula. We got to have our lowest whole number ratio. And these aren't whole numbers. So remember our steps, we divide by low and then we multiply to try to make whole. So we would divide by the lowest subscript, so we'd find the lowest subscript, that one, and we divide each subscript by that, okay? Now this one's a little tricky, okay? When we divide the carbon, obviously we get 1, but when we divide the H, we get like 1.34, 1.33, 1 1/3. And then when we divide the oxygen, we get 1.165. And that's not close enough to 1 to round it down to 1. So this is what I got. And so I still don't have whole numbers. But I'm going to let this 0.33 be a clue. If I have a third, how do I make a third a whole? I multiply by 3. So I'm going to take these subscripts now and I'm going to multiply by 3. And this is what I get. I get C3H4O 3.5. Well, 3.5 I can't round, okay? I can't round that up to 4 or down to 3. So I'm still not whole completely. So, but if I have a half, now I can multiply by through by 2 to make everything whole. So I'll multiply this by 2, and now I have all whole numbers, and I can't reduce that any further, right? Because that's 7 there. So 6, 8, 7, those are my subscripts, and because that is the lowest whole number ratio, that would be my empirical formula for citric acid. So C6H8O7. And I know what you're saying. You probably could have just Googled the formula for citric acid, but you don't have Google available on the test, or you shouldn't. If you do, remember I know where you live. All right, so there we go. That's the empirical formula. All right, so based on the initial information of the question, that's all I could really figure out. Okay, the empirical formula. Okay. Now, in part B, we want to determine the molecular formula, but remember, if you want the molecular formula, the other thing that you need to know is the molar mass of the compound. Okay, the molar mass of the compound. And so sometimes they just say, hey, here's the molar mass of the compound. Now find the molecular formula. In here, they don't quite give you exactly the molar mass, but they give you a way to figure it out. All right, so they tell you that 10 grams, in another experiment, it's found that 10 grams of citric acid is equal to 5.20 times 10 to the negative 2 moles of citric acid. So that's our key to get the molar mass. And once we have the empirical formula and the molar mass, now we can find the molecular formulas. So let's go back down to where we were at. Okay, all right. So what we need to remember is what molar mass is. It's grams per mole. And so if we take the grams that they gave us in part B and we divide it by the moles that they gave us, that gives us grams per mole. So the molar mass of citric acid comes out to be around 192 grams per mole. All right, so now what we're going to do, so that's the molar mass of the compound of the molecular formula, and we're going to compare this to the molar mass of the empirical formula. So if we add up 6 carbons, so 6 times 12, or 6 times 12.01, 8 times 1.01, and 7 times 16, and we add that all up, it comes out to be 192. Oh, yay. All right, so that means that the empirical formula is the molecular formula. So remember, when you find this, maybe the molar mass of the empirical formula will be half the molar mass of the compound, or it'll be 3 times less, or 2 times less, or 4 times, whatever. But when the molar mass of the compound is the molar mass of the empirical formula, that means that the molecular formula is the empirical formula. So we just verified that the empirical formula is also the molecular formula. So that's part B. Okay. So what we would do is you would take the molar mass of the compound divided by the molar mass of the empirical formula, and that should come out to be a whole number. In this case, it comes out to be 192 divided by 192. So you would multiply your subscripts by 1, and you get the molecular formula. But if they were different, hopefully when you divide, you get a whole number. You'll either get 1, 2, 3, 4, 5, 6, 7, and again, we're just rounding. So when you divide, it might not be exactly 4, but it might be like 4.001, like close enough to 4, 3.99 or something like that when you do it. All right. So that's the molar mass, that's the molecular formula of the compound. So now we can balance the combustion reaction, right? So whatever formula we got for the molecular formula, that's what we would put here. And then we would say plus O2 yields CO2 and H2O. So remember how we balance a combustion reaction. The first thing I'm going to do is I'm going to put because I have 6 carbons, I'm going to put a 6 here to balance the carbon. Because I have 8 hydrogens here, I'm going to go over here and put a 4, because 4 times 2, that's going to give me 8 hydrogens. Then what I do is I add up all the oxygens on this side. So I have 6 times 2, that's 12 oxygens here, but I have 4 times 1, that's 4. I have a total of 16 oxygens on this side. Now, because I have oxygen in the citric acid itself, what I have to do is take that total and subtract how many oxygens I have here. So 16 minus 7, because I have 7 oxygens here, that gives me 9. So 7 of the 16 oxygens are coming from here, and so that means 9 of the oxygens have to come from here. So because that's O2, we'll take our 9 and divide it by 2. And if we put a 4.5 here, that's going to be 4.5 times 2, that's going to give us 9, plus 7, that'll be 16, and that'll match the 16 oxygens over here. So we got 1, 4.5, 6, and 4. But to be properly balanced, we can't have fractions. So now we'll just double everything. And so it would end up being 2, 9, 12, and 8. And that is our balanced equation. All right. So hopefully what I just did there made sense. I mean, you can just go back and forth and balance, but this is kind of a systematic way of doing it for combustion reactions. Okay. If we didn't have any oxygen here, we would just take the total, divide by 2, and put the put the coefficient there. But because we had oxygen here, that's why we did that subtraction first before we divided by 2. Okay. All right. So part D is just a stoichiometry problem. So now that we have our balanced combustion reaction, it says how many grams of oxygen are going to be required, what mass of oxygen is going to be required to completely burn 30 grams of the citric acid. So we would take our 30 grams of citric acid divided by the molar mass of citric acid, then times the mole ratio, 9 moles of oxygen for every 2 moles of citric acid, and convert to desired units. We wanted mass of oxygen, so O2 is 32 grams per mole, so multiplied by the mole mass. It's just a coincidence that it comes out to be 22.4, okay? I didn't plan it like that, it just happened, okay? So when things like that happen, you say, boom, baby, and you nailed it, all right? So 22.48 grams of oxygen to completely burn 30 grams of citric acid. All right. So hopefully